Start streaming. Now, whose books do I still have? Heather, Samantha, Jensa, Riley, Hyundai, Josh. Your book is here. Kate. Your book is here. Ned. And how dare he? How dare he? Silly, silly. So you got together with someone, got the homework, got the notes. Oh, then attempt to do the Lewis dot diagram for nitrogen. Do you remember Lewis dot diagrams from last year? Just try it with nitrogen. Do you remember the accounting system with electrons? Okay, then definitely just start with nitrogen. The accounting system is when you yeah, so you count up the total. So just make sure you're adding up the right number of electrons. Yeah, just start with nitrogen, and then I'll go over them, and we'll probably get somewhere from there. Also, as you switch to this one, I'm going to give you the skeletal structure for this one. One thing to know, this is an organic molecule. With organic molecules, the central atom is always carbon. Then they're both central atoms. So what I'm going to do is give you the connectivity, and then you can try and figure out if there's any double bonds where it goes through. So for carbon, it would look like this. I am only putting single bonds in. I'm only showing connectivity, but notice the carbons are attached. It would have an oxygen there and an OH there. Oops. 1 second. So use that as sort of a guideline. Oh, they took it off. Here, why don't I send it to you? It's on this one, so I'm going to go to here, forward. Okay, is it popping into your email? Dun, dun, dun. Also. Okay. I was also going to text it to you, but if you've got it. Okay. Those aren't on Google Classroom. Those are notes. Yeah, no. You'll need do you have a drawing ability on that? Are you're no longer tied up with your hand? Oh, okay, yeah, get out some paper. Oh, it's terrible. Did you do Lewis dot diagrams at all last year? These are Lewis dot diagrams. Now, I don't know if you did them in the same kind of way. Well, it depends. Did you do it where you like would keep track of your electrons and add them in around a central atom? Or did you do it like you would make the Lewis dot diagrams and join them together? Ah, that is one of two methods. That works well for some things, not as well for others. It actually works really well for things like this one, and not so well for some of the later ones that we're going to be doing. Well, why don't I do this one with you? Like, I'll just redo it. While everybody's starting on the new stuff, I'm just going to, I'm going to ask you questions. So let's do the CO2. So, I came up with a bunch of rules, but I'll just do it, and the rules will be sort of self-explanatory. Number one, you take all the valence Can you see? Okay. Yeah. Where's your glasses? Why not? Where is your contacts? Okay. New contacts? Yeah, okay. Yeah, fair enough. How many electrons does carbon have? Valence electrons. Yeah, 4. And then 2 oxygens. Valence electrons and 2 oxygens. 12. Now, if this was plus 1, this area is for the charge. So if I put plus 1 there, what would that do to the number of electrons? Decrease them by 1. If this was minus 1, I'd add 1. And so this spot is for that. So that 0 was there not for oxygen, but to say that there was no change due to the charge. So it's 0. Add them up, we got 4 plus 12. So we got 16 electrons. Now, the method that I've been using is you take the central atom. Which one of these is the central atom? Let's see. Put the central atom down, and then you put all the other atoms around it and join them. So you go O, O, and join. No, not quite it, but that's like the second step. How many electrons are in those bonds? Four, because there's always 2 electrons per bond. So I minus those 4. This is the accounting part. So I got 12 electrons left over. The next step, I'm going to remove that away because it's making my bond look silly. The next step is you give the outer atoms, not the central, the outer atoms, their full octet. One at a time until you run out of electrons. So I would start here. How many electrons, how many electron pairs am I going to need to give oxygen? 3. So I go 1, 2, 3, 4, 5, 6. And I minus those 6. How many do I give to this oxygen? 3 pairs. And then I minus that 6. And then I get to 0, and I'm not allowed to add any more electrons. I am out. Now, at this point, I then look at the central atom and say, is the central atom happy with an octet? Is it? It looks kind of sad. How many electrons does it think it has? 4 valence. It has 4 electrons in bonds. So it needs 4 more. So the rule is if your central atom doesn't have enough, you borrow from the lone pairs next to it, from its neighbors. So you take away 2 and turn those into a bond. So they just sort of slid down. Is it happy now? Nope. So you keep giving it bonds one at a time until it's happy. So I'll take 2 from over here. Is it happy now? Yeah, then it's done. So that's how I got carbon dioxide. So go through the same process for nitrogen. Now, if you want to sit next to someone because you don't have the notes so you can get those rules or something, that can work too. Okay. Reminder, put away your laptops once you're done the form. Oh, they've closed the door. I'm thinking they're good. Where's nitrogen? Nitrogen. Why do you have business cycle? There's no business cycle. First of all, it's literally just made up. It's nonsense. No. Economics just make everything up. It's all a form of conspiracy theory. No, they make up terms. But if you ask an economic, no, because we actually measure our things. Is money real? No, it's not. And so the problem is every time they measure something, they actually change what it is. It's like quantum, but worse. You're doing well. However, you're not using the method I showed. However, let's do that again. But you're sort of using both methods. So what I would do, you've got 2 ends, which are 5 each. It's 10 electrons, right? Now, why did you minus 2? Oh, that's fine. Okay, let's do that, though. Erase all of that, put the nitrogens together and give them 1 bond, and then minus 2. That's perfect. But take away all those lone pairs, because you haven't done that yet. You've only minus 2. So take away all those lone pairs. Yep. You don't need those. Perfect. And make sure that looks like a single bond. Like, erase it thoroughly so that you only have 1 line there, so we know what we're doing. There we go. 1 bond. Excellent. Now, the next part of the rule is you give the outer atom its full octet. And you get to pick because they both look the same. Yeah. Until it has 8, yeah. There you go. How many did you use up? Yeah, minus that. Yeah. And then you take whatever you have left over, put it on the central atom. Excellent. Are any of them unhappy? Yeah, so what do you do to make it happy? Yeah, and then erase some of the lone pair you used to make the bond. Hold it. You erased one of the electrons there. Why'd you do that? Because you erased one of them on here to make the bond. You don't erase the one there. It's the one that wants electrons, right? Now, is it happy now? No. Yeah. Yeah. Oh, no. That's 4 more. Yeah. Yeah. So you got 1, 2, 3. And then each has a lone pair. They each think they have 8. Yeah. So that's it. You made a triple bond. Yeah. Yep. That one, not so much. That one, you've sort of given them, you can keep going. Well, are they happy? Do they have 8 each? There you go. You have 2, 4, 6, 8. You have 2 fewer. Where's your electron accounting? Get that down. No, I want to see electron accounting first. Ooh, Ooh, I like that. I think you have too few. You have 4 electrons left, right? So you put them on the outer atoms. Carbon are central atoms. Where are the outer atoms that need electrons? Yeah, so use them up. Put them on there until they have a full octet. That only has 6. 2, 4, 6, 2, 4, 6. They each have 6. 8. Yeah, so use them up. Yep, and now you have to do something. Where's your nitrogen? N2. I just want to see that one. Make sure everybody's looking. Oh, it's looking good. N2. Nice. Okay. Yeah, looks great. Oh no, that was just to give you the skeleton. So that so you knew what attached to what, because it's a more complicated molecule. Yeah, that looks awesome. You're on your way. Okay, but this one's not quite done. Are those nitrogens happy? Two, four, six. Oh, I see what the problem is. Where's your electron accounting? Oh, there it is. You have 10. You minus 2. You had 8 left. Okay, you have 10 electrons, right? 2, 4, 6, 8, 10, 12. You have added an extra 2 electrons. Counting went wrong at some point. Language. Excellent. Something's wrong with this one. Yep. I'm 100% sure. It is almost entirely correct. The bonds are fine. Nope. Nope. Why are these separated? Yeah. We only put electrons on in pairs, unless we're making individual ones. And so they should be paired. Okay. Yeah, that's perfect. That's awesome. You did everything exactly right. It's perfect. What's wrong with it? How many electrons do you have? 18. 18 looks good. How many electrons do you have? 2, 4, 6, 8, 10, 12, 14. 2 carbons is 12. 1, 2, 3, 6. 12, 14. Hold it. 1, 2. Oh, I know what we did wrong. How many electrons are in 2 carbons? It would not be 12. How many valence electrons are in 1 carbon? Yeah, that's what you did. Yep. Put away phone and bag so it's not a temptation. One more step. One of them's unhappy. How do you fix that? Oh no, I'm asking you. That was my reverse. No, that was my reverse Uno card. Like, back on you. Yes, it does. I want you to stare at it and feel frustrated. Where? Hold it. Actually, no, there's something that's not quite correct. This one is a little off. I didn't say that those were wrong. Let's take a look. You got 8. And hold it. That's not for this. You got 5. 18 minus 1. That's perfect. Oh, hold it. Yeah, what is... That's 24. So you have another 2 electrons at the bottom. So put the oxygen back there. And you just... Yeah, there you go. Okay, now you're good. But there's one more step. This one's unhappy. What do we do when the central atom is... Yeah. And then where did those electrons come from? You have to get... Oh, you already got rid of it. Perfect. Yeah, that's great. See? You did know. You can do it that way. Hold it. Are you working on the last one? Yes. It helps you to know the overall structure and where those oxygens should now go if you're going to drag them in like that. How many electrons do you have? Where's your accounting? Yeah. And then you put the 10 in. Did you use them up here? Why'd you put them on there? Yeah, but it's a central atom, so you don't put it on the central atom. You put it in the outermost atoms first. Good instinct otherwise. Yeah. Perfect. Now everybody's happy except for that carbon. Where are you going to get... There you go. I think you're on the right track now. Yeah. 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 And then you're done. Yeah. How you doing? Where's your answer? Oh, that looks good. That looks good. The math part? How many electrons are in those bonds? Yeah. Sorry, what? No. No. How many electrons are in a bond? 2. And how many bonds you got? Nope. 7. So 7 times 2 is how many electrons? 14. Minus that from your 14, and how many electrons you got left? 0. So you're done. Do they all have, does the carbons both have an octet? Yeah, they're good. Does the hydrogens have as many as they want? Yeah. So you are done for that one. This one needs another step. Are any of these unhappy with their octet? Yeah. So what do you do when they're unhappy with their octet? Yeah. So erase 2 and give it a bond, and then see if it's happy now. Oh, not those 2. That's the one that wants them. You take it from the one that has too many. Yeah. Yeah. Is it happy now? How many does it think it has? Right. Is that happy? No, because it needs an octet, so do it again. You just keep going until they're happy. Is it happy now? Yeah. Is that one happy? Yeah. That's you're done. Yeah. So now you can start on that one. Okay? Okay. I'm going to take away this. I think I've had a chance. Is there anybody who's N2 I have not seen? That I should. Whose? I haven't seen yours? I saw that one, and you're doing a good job, and that one looks good. So you're good. Okay. A reminder, the counting system is important. So you have 2 nitrogens. Nitrogen has 5 valence electrons, so you have 10 electrons. There's nothing else. Put it down with a central atom. And the students at this point go, well, which one's the central atom? And the answer is, well, they're both the same, so you get to pick. You make a bond, minus 2 electrons, 8 electrons. I'm going to say that that one's the central atom, so I'm going to give the electrons to the other one. And I do it until it has got its full octet. That took up 6 electrons. I got 2 left over, so I put them on my central atom. So when I'm coming around to look, I want to see it all the way down to 0, so you know when to stop. Because what can happen is students just keep going. They go, oh, well, I need more electrons. You have stolen from the electron bank. There isn't that many electrons. That does not exist. And then, of course, what do you do when the central atom doesn't have enough electrons? Borrow some. Yeah. Please, sir, can I have some more? And then the nitrogen next to it is like, sure you can, Will. What is the name of that child in that movie? Oliver Twist, that's the movie. Yes, Oliver, you can have some more. Yeah, it was. I'm just being a little nicer. Yeah. And then we go, is nitrogen happy now? No. Oliver's like, it's not enough food. This is only half what I need. It's actually 3/4, you greedy little. So you erase another one, put it in, and then Oliver, thank you, Jeff Bezos. And you're done. So that's what it looks like in the end. So we have made a triple bond. Next up, C2H6. Now C2H6, I'm going to show you this because these are going to come up. We're going to do organic chem at the end of the year. Your book gives you they give you the overall structure, and I don't know why they do it like that. It makes it a little, in my opinion, too easy. It also can make it a little too confusing because you think they've done it for you and they haven't. It's actually easier if you start from the beginning, but that aside. Carbon is always the central atom because this is organic chemistry. Organic does not mean what it means at the grocery store. Grocery store is a completely different thing. I'll get your questions in a moment. I worked for my uncle's turkey farm while I was in third year university. I was doing a work term at UBC, and someone phoned me up, and I was answering the phones. I don't know why he let me do that. And a lady asked, is your turkey organic? And I said, of course the turkey is organic. It's a turkey. And she says, no, I want to know if it's organic. And she just emphasized the last word. And I said, well, the bones aren't organic because they have calcium, I guess. And the salt in the bird would not be organic. And then she got very angry and then hung up. In chemistry, when I use the word organic, all I mean is carbon chemistry. Carbon is joined as a backbone. So whenever you see a carbon compound, just line up the carbons in a row. For now, that'll work. And use them as the central atoms. You just have to kind of change the procedure a little bit and know that there's more than one central atoms. I also almost got kicked out of an organic food store in Victoria. In my defense, they had a sign and it said organic salt. Salt is a rock, a literal rock. If there's one thing that can't be organic in any definition, it would be salt. But my wife I said that very loudly a couple of times, and then my wife asked me to leave because she just wanted to buy some hummus, and they have very nice hummus there. So the places who don't know organic chemistry seem to have the best hummus. I don't know what is up with that. Okay, questions? Yes. There cannot be. Never. No, you can't. Highly reactive. But it's not, it can because the procedure I've given you, so if you just had C2, you'd think like it can be, right? But because the procedure I gave you doesn't take into account the actual physical structure of the atoms, it's just a method by which that usually gives us the correct answer. And I can show you why not. We have some literal models, but that's not good for this, even though these are smaller. So here is C2. How many electrons are in 2 carbons? 8. So I have here 1, 2, 2, 4, 6, 8. And that's it. There's my last bond. So I'll put it on this one. Now, here's the bonds I could have. I've got one bond between them. I put everything on the outer atom. And I'll make this one of these longer bonds, just to make it fair and easy to see. We will hopefully be playing with these at the end of the year. You'll get some molecular model kits. So here's my C2 atom, or molecule. Can I join and make a double bond? Yes. Is this one happy? No. So I make another one. Now, although this is a physical modeling, it actually models really well because these are under stress. Because they are literally moving like this, like they're bending over to join. And that is actually, this is why molecules with a CC triple bond are incredibly unstable. But it will work. Where's the last bond? It's there. And that literally cannot reach. There is no way for this bond. It's so energy intensive, it is impossible. It cannot physically construct itself. It is like Miss Hanley trying to reach items on the top shelf. She's just like, too short. Oh, she's the assistant librarian. She's now you know her. Yeah, she's also my spouse. So yeah, when I want Lisa Miss Handley, should be respectful, not to have something, then I just put it on the top shelf because there's no way she can reach. Yes. 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 So when you put the lone pairs on, so way back here, when I put the lone pairs on this one and I ran out, I put on 6 and then I took them away. And then I put the other lone pair here, I minus the 2, and that's how I got to 0. So when you're putting the electrons in the outer atoms, you put them on in pairs, and as you work through the atoms, you should be minusing them. That tells you when to stop. And that, because if you didn't stop, you could just keep adding electrons forever. Yeah, the electrons just boom. Not allowed to do that. Okay, C2H6. Central atoms are carbon. Oh, first we'll do this. 2 carbons have how many? I just did that. Nope. 8. 6 hydrogens have 8 plus 6 is 14. So what we do is these are our central atoms. And in this case, we have to kind of fudge it a bit because we have 2 central atoms. And we just put the hydrogens around them. And join them up. How many bonds did I use? 7. 2 electrons per bond. Minus 14 electrons. 0. Are any of them unhappy? We're done. The E isn't happy. This is sad E. Carbon each has an octet. Hydrogen has its 2. This is ethane. You've heard of methane gas? Methane gas is like this. This is ethane gas. If you wanted to make propane gas, so you wanted to burn on a barbecue, propane gas is just like this. When you burn propane gas, that's all you're burning. 3 carbons. Burning propane gas? Oh, no, we learned the names for all these. So you'll learn methane, ethane, propane, butane, pentane, hexane, octane, nonane, and decane. If you notice, once you get to pentane, it's easy because it's pentane, octane, nonane, like it's 5, 4. It's methane, ethane, propane, and butane that have the slightly weird ones, the first 4. And then we learn how to name alcohols from that and everything else. It's organic chemistry is the best chemistry. Okay, NO3 minus. Nitrogen, 3 oxygens, and a -1 charge. This row is for everything that affects the electron. So I take the charge from here and I put it there to remind me, what do I do with that? How does that change the number of electrons? +1. 3 oxygens have how many electrons? Nitrogen has, Cahalan? Five electrons, excellent. You were looking at the other one. Add them all up, we've got 24. Put nitrogen in the middle. Atoms around the outside. Bond them. How many do I take away? Sasha? I thought you said the answer, so I was just Oh, okay. Minus 6. Down to 18. And at this point, I see students who really, really just want to do that because I see an empty spot. You are not filling empty spots. You are filling the outer ones first because that's going to lead you to the double bonds. And you do them one at a time. 1, 2, 3, 4, 5, 6. That is an octet minus those 6. 12. 1, 2, 3, 4, 5, 6. Minus those 6. 6 left over. 1, 2, 3, 4, 5, 6. Minus those 6. Now we're done. We cannot add any more. I know that I cannot give 2 electrons here. What do I have to do? Make a double bond. Thank you. So you take 2 electrons away. Does it matter which one? No, because the whole thing can rotate. We're drawing it in one particular direction. But of course, in real life, this is a molecule flipping around all over the place. Yes? Oh, one thing, so like you're saying, like, why is this a T shape? Why isn't it bent or something like that, right? Yeah. So first of all, yes, you can. In real life, these will all be equidistant from each other. So this bond, this actually wouldn't be a T. These would be, what's 360 divided by, these would be 120 degrees apart. So this should actually be further down. And we haven't done that yet because we haven't done structure. But generally space them out so they're equally distanced and you'll have close to the right answer. But you also have to remember this is going out in 3 dimensions. So for example, when we draw it like this, so if I drew this, are these 90-degree angles? No, what are they? Yeah, they're in a sphere. So these angles, oops, get that one, are approximately 109 degrees because they look like this. They're not flat. If these two are going sideways like this, these ones are going like that. So this is CH4, what I've drawn flat. What I've done is I've forced them to go like this, which I can't really show very well. But I've made them a flat plane, and it doesn't even want to stick. And if I try to make it a flat plane, they'll just slide over because they want to be, electrons repel each other, so they want to be as far apart from each other, so they're going to use all 3 dimensions. Does anybody know what kind of shape this is called? A 4-sided shape? A square in 3 dimensions is a 6-sided shape. Does anybody play D&D? What's a 4-sided die called? 4-sided die. It is a triangular prism. This is known as a tetrahedron. Tetra meaning 4. It's got 4 surfaces on it. 1, 2, 3, 4. And that's the shape. This is the shape behind biochemistry, because that's what these are the chains that carbon makes. So the chains that carbon makes tend to go like this, and why they get tangled up in the way that they do. So do be aware that the ones that I am drawing are 2D representations, and we haven't done shape yet. Okay. Oh, we will care. It's called VSEPR, or VSEPR. We don't care yet. Now this is one that if you do it kind of like the central atom, it can still work. You do have to realize those are the central atoms. Carbon, I'm doing it in red. Why am I doing it in red? And I'll get out of your way. I just realized I've got 4 I haven't done my accounting. I've got 2 carbons and 2 oxygens. Electrons from 4 hydrogens. Keith? 4, excellent. Electrons from 2 carbons. Jonathan? Excellent. And from 2 oxygens? Sorry? 12. Add them all up, we get 24 electrons. Now let's join all of these with single bonds and see where we end up. So, I said this is the overall structure. Oops. That oxygen's looking really tiny. And then we'd count the bonds. 1, 2, 3, 4, 5, 6, 7. So minus 14 electrons. I've got 10 left over. Who should I give electrons to? Oxygens. Why not carbon? They're the central atom. So we start here, give it an octet. Minus 6. Give this one an octet. And we're done. Anybody unhappy? Yeah, who's unhappy? C. So how are we gonna fix that? Which oxygen? Take from this oxygen? Oh, that's brilliant. It's wrong, but it's brilliant. Yeah. Oxygen won't do that. It just won't. It already has a bond on the other side, and you wanted to end a bond on this side, and you wanted to give it a third bond, whereas this one is here doing absolutely no work. Yeah, the other one will. Yeah. And this is one of those, if you did that, especially now, I mean, I wouldn't mark you wrong right this moment because I haven't told you that. But this one is just more likely to do that. More likely. It absolutely will do that. And the other one absolutely will not. And that solves the problem. The reason this one won't do it, as we can see, we can kind of get it from their Lewis dot diagrams. The Lewis dot diagram for carbon is 4 dots. What is the maximum number of bonds that carbon can have? Are you off? Oh, okay, perfect. Okay, thank you so much. So carbon, with its 4 lone electrons, can never have more than 4 bonds. The Lewis dot diagram for oxygen looks like that. What's the maximum number of bonds oxygen can have? Using the same logic. 2. Oxygen will bond here and here. It doesn't want to bond with those. Hydrogen will only bond once because it's happy with 2, and there it is. So these actually form part of the rules of how you bond things together. So if you're ever like, can this have more bonds? This can help you, especially with ones that obey the octet rule. So oxygen will not bond more than twice. To the point that if they make molecular models, the molecular models of carbon have 4 flat surfaces. They don't make oxygen have 4 flat surfaces. They just give it 2, because if you've bonded it more than twice, you've done something wrong, and they want to make sure students don't do something wrong. So there's water, but we cannot make the equivalent of methane out of it. There's no spot for it to bond. I'm so excited that I learned that these stick to the board now. I know. I was like, woohoo! Okay, exceptions to the octet rule. Notes. But like 5 lines of notes. It's 5 lines. Yeah. So how I've been telling you, like the octet rule. You know hydrogen. So there's only 2 more. It's beryllium and boron. Beryllium is happy with 4 electrons, so that's like up to 2 bonds. And this means that's bonds and lone pairs. So beryllium could have 1 bond and 1 lone pair. That's fine too. It's just a maximum of 4 electrons. Beryllium and boron are here. So hydrogen 1 bond, beryllium 2, and boron 3. And you may be thinking, but Mr. Neufeld, beryllium's a metal. Why would it engage in covalent bonding? And I would just encourage you not to think about that. Because it just does. Elements above phosphorus, and these are always going to be central atoms for us, so you never have to worry about outer atoms breaking the octet rule. But our central atoms, phosphorus and above, so phosphorus, sulfur, chlorine, sodium, bromine, iodine, can all have more than an octet if they need to. They use their D shells. So phosphorus that is way up here, that has no d electrons, what's its why did I do that? What's its energy level? What orbital is it in? Which one? P? Which P? 3. 1s2, 2s2, 2p6, 3s2, 3p. 3p. Because it has 3p, although they're not filled, it's access to the 3d. It's in the same energy level. So it can use those spots if it needs to create more bonds. So an electron comes along, if an element comes along with a lot of electrons and is looking really attractive, phosphorus can say, come on in. I have room for lots of people. And just fill up with more than 4 bonds. P up. P up. So starting from phosphorus, everything after P. Yeah. Yeah. So essentially, what obeys the octet rule are those ones. Carbon, nitrogen, oxygen, and fluorine. You'll find that chlorine often does too, but it doesn't have to. It only happens if they're the central atom. The outer atoms will be fine with their octet, but if you have to take more, if they're the central atom, they will. So, there we go. I'm going to then add to here. We have some for you to try. Everybody done writing this down? Anybody still need some more time? Okay. This first one, not an exception. It's just to get your skills back going again. Then there's some exceptions. Then there's some normal ones. And I'm adding to this because it's fun. Because I should have put that one in. And then when you're done those, I'm going to put challenge. But challenge doesn't mean optional. I still want you to do these. But these are just a little bit more difficult. Yep. I'd highly recommend you do that. Yes. Just because I add some charges in those. Some of them break the octet rule, some of them don't. They're just interesting. Work on those. I'm going to go check the other room where the Zoom conference is going on. I'm going to come back. I'll wander around, see what you're doing. Show me your CHO2. Remember, what's the central atom in the first example? C. So attach everything to C. Organic chemistry, carbon's the central atom. Or a chain of carbons if you get that. other two went to a breakout room. Do you know which way they went? Oh, okay. Okay, I'll just look around. I always start on that side. I should start on this side today. Oh, that's a 4. What did it look like? It looked like a Y. Oh, well, that makes sense. There. A very clear 4. Where's your periodic table? Like your paper one. No, but if you had the paper one, it would be literally right in front of you. Yeah, you wouldn't even have to switch. But if you're already tabbing, then you're already moving away from the screen. Here. Because the other thing is, what are you gonna use on a test? But I want you to get used to this one. There you go. Mm-hmm. Mm-hmm. What? Which one's an exception? Oh, no. When C bonds 4, it has 8 electrons. 2, 4, 6, 8. Yeah. And oxygen still has an octet. It always has, if it bonds twice, it always has 2 lone pairs. Yeah. So that's how they deal with that. Mm-hmm. You should never have a lone electron. I don't know how you got that. So, oh, I know what you did. Erase that. We're just going to start over. You're very close. I feel bad erasing it. Erase all your accounting. Erase that. And erase the line, because you forgot a line. You forgot the line for the charge, right? -1 underneath the 2 oxygens. And then what does that do to the electron number? Yeah. Perfect. Now add that all up. And then do the whole thing, and you'll probably get a dead on. Do the accounting part first? Awesome. Perfect. These ones. Have you got those ones down yet? Well, it doesn't have an octet yet, though. Oh, it is. I just want to make sure if you knew that. Huh? Tricky. I also like how in all of my classes, it's like half the people have spontaneously decided they're going to use the German method and use lines. I don't disagree. I like both. I happen to use the dot just because that's the way I was trained, but I've never before had classes. I've taught it the same way before, and never before they spontaneously like, yes, we will use lines. We are also German. Yeah. That was right. Yeah. Sorry, you were trying to ask a question. Ooh, something interesting has gone on here. Why are they not all attached to the central atom? Why did you attach the chlorine out here? No. So one rule is, if you have a central atom, you have to attach everything to it. So restart the accounting, restart that process. I didn't teach you any exceptions. And I think I may have mentioned the lines, especially if there's someone who's German in the class. Oh, I showed it to people last year. I didn't, but I've always done it with dots. Did you grow up reading the Berenstain Bears? Oh, then this analogy wouldn't work. However, does anybody else grow up reading the Berenstain Bears? Yeah. Yeah, the universe jumping. Joshua, how do you spell Berenstain? Just the last four letters. No, that's Stein. You're reading R.L. Stein horror novels, apparently. Yeah. Is anybody else with a spelling for the last four of the Berenstain Bears? Yeah, it's not. If you look it up on Google, every book ever sold is they're Stain, Stain. However, everybody has a collective memory of it being the other way around. And it's just a thing. It's like how when I was growing up and it was the 90s, everybody knew that Nelson Mandela was dead. He had died. That's the Mandela effect. He wasn't dead. We all had the collective memory that he was. And then when we actually died in 2003, we were all very shocked. Wasn't he already dead? And so you have a collective memory, probably because you used it, of me teaching it that way. But I didn't really. But they're both fine, so that's fine. No, they never, no. He was in prison for a while. Not one that I ever saw, but there could have been one around the world. The Mandela effect is named for the fact that there is no actual good reason. It's not like everybody in the world was told he was dead at one point and it made the news. Like, it actually just never happened. And there might be something a little monocultural and a tad racist about it, because people in faraway places who, like, we don't think about every day, oh, they must have died a long time ago. Like, we just do that sometimes. Yeah. Louis C.K.? Martin Luther King? Yeah. MLK. Yeah. And, well, that's the... Yeah, and then they go, oh, well, they must all be dead. Yeah. Okay. Back to chemistry. Yes? Yeah. Pablo Picasso was contemporary with, I don't know. Sorry. The name just accepted. He was a famous guitarist who played at Woodstock. And they met each other even. And people were like, what? We thought he died like ages ago. Okay, sorry. I'm distracting people. Oh, for this one, the first one, for all of them, you take the central atom, put it in the middle, and arrange everything else around it. So these have no funny ones. You put carbon in the middle, and you put hydrogen and oxygen around it in 3 separate spots. And if you are joining chlorine to chlorine or fluorine to fluorine, you are doing it incorrectly. They all get joined around it. You have miscounted your electrons. There's no way you should have one left over. Where's the counting for the charge? Ah. Oh, yeah, boron's an exception. So, oh, you're thinking beryllium. Beryllium can, you might have. You forgot, oh, beryllium is, I think you wrote it down backwards. Let me put it up, and then you can quickly correct it. Tell me when you got it, and I'll flip it back. Good? Okay. You have too many or too few electrons. You have a lone one right there. You also, oh, why did you, oh, how did you, okay, erase all the electrons. No, it's fine. Um, so you minus the 6, erase everything after, like keep that 12, but erase everything else. Now what you do, because you were being very egalitarian, you were sharing them equally. No, we're not communist yet. What you do is you give one of the oxygens a full octet, like everything at once. Minus that. Minus that from it. Okay, now give the other one a full octet. Minus that. Now you're out of electrons. Yeah, there you go. Yeah, you erase on whichever one you're bond, you're going to erase one. Take away an electron. So you, yeah. You have to add an electron. Yes, exactly as you did. No, because what we're just adding up the valence electrons, but these electrons, notice we're not giving them to anybody in particular. We're just following a set of rules. So we now, this is like we've pooled our money together, and we're going to go buy dinner for everybody. Now, once you've pooled it together, no bill belongs to any particular person. It's just a pool of electrons that you can use. Yeah. Yeah, perfect. How are you doing? Okay, see? Just move your hand a little bit. Excellent, that's awesome. How are you doing? Oh, those are looking lovely, except your chlorines are confusing me. Did you forget to put a line there because it was a CL? Or are you missing a line? Why did you do that? You can keep minusing too, yeah, and keep going around. You'll get there. And how many did you use up? There you go. Take them away. You're done. Is any of them unhappy? No, you're good. But the way I would recommend doing it, because this still works, so there's nothing wrong with that, is when you have all of this, give one of them all of its octet, minus it, and then go to the next one, and then give it all of its octet. Don't try and be even about it. Mm-hmm. Yes. Sulfur, yeah. Well, this had 5 chlorines and just 1 phosphorus. Yeah, so sulfur. Because sulfur is beyond phosphorus. Oh, no, it's 5 plus. They can actually, you will see ones with up to 8 commonly. Yeah. Hmm? Which one is a piece? So, phosphorus in the middle and put chlorine all around it. Give yourself a bit of room, though. Yep. You have to. Give yourself room. Like, make the chlorines a little farther away. There you go. Did you say how? With a pencil, you just write it down. Well, you minus your 10. You've got 30 left, right? Yes, because phosphorus is our exception. Yeah. Yep. Now, don't be egalitarian. Are you like don't worry about that one yet. You put 2 down here and there. What I'd rather you did is give it all 8 it needs and then minus that. So you used up 6, minus that 6, and then give the next one 6, minus that 6, and just keep going. Anybody with hands over on this side? I will walk back over. Sure, yes. Yep, that is right. You did. You have too many electrons. You have too many electrons. How many do you have from 3 fluorines? Nope. How many electrons does fluorine have as a valence? 7. Not the number of protons. Valence electrons. Only the ones on the outermost shell. So you should only have 21. You have too many. That looks good. How'd you get 50? So over 6 plus 42 is 48. It's okay. Lots of people have been doing that. This looks great. That looks good. Where's your PCl5? That looks good. And then something, that looks cool. I actually put that down. I haven't done it myself yet. I think that is right, though. It might not be, though. Because I think, if my memory serves me correct, I haven't done it since a little while ago, but I think it has a lone pair there. But let's count the electrons. Nitrogen has 5. Yep. And what's the charge in the whole thing? Is there one? And then iodine is 7. 3 7s are 21. 5 plus 7 is 26. You have 26. And then you minus 6, so you have 20. And then 2, 4, 6, 8, 10, 12 is 18. Oh, you would have been able to put an octet on here without resorting to a double bond. Oh, you put a double bond and you have that. Ah, that's what you've done. Don't do that. Whoops, no, I just did it again. You were at this, right? Minus those lone pair electrons. Like, how many is that? 18. Minus that 18. The last step is if once you filled it up, if it's full, you don't make double bonds, you put it on, because that would give this one more than an octet. You just put it on, just like that. Yeah, that's perfect. Okay, it's 1:14. I'm good. You've done a lot of good practice today. Thank you very much. If you haven't finished